Welcome back, everybody. This is notes number 27 today. We're midway through chapter 5. We are going to be going beyond the book in chapter 5 and doing some pretty incredible problems. But today we're on section 5.5. We're going to learn about synthetic division. That sounds a lot like synthetic substitution, doesn't it? And we're going to learn a couple of theorems. One of them is called the remainder theorem. Okay, first of all, let's do a quick review of synthetic substitution that we learned last time. So this is an alternative to direct substitution if you're looking for a function value like f of -4. Instead of just plugging in -4 and computing, what you can do is put -4 in a box, put the coefficients of the polynomial in a row, so 2x cubed, 3x squared, -10x, and -6, and then bring down the first number, multiply by the number in the box, write it down, and add the column. Multiply that by the number in the box, write it down, and add the column. Multiply that by the number in the box, write it down, and add the column. And what that tells us is that f of -4 is -46. If you think about that graphically, that means that this function, whatever it looks like, goes through the point -4, -46. Okay, so let's get ready for today's lesson. You don't have to write this down, but we're about to do what we call polynomial long division, and so to justify the process, I want to remind you of long division that you learned with numbers. So let's say you have 2,306 and you're going to divide it by 34. And you're not using a calculator, you're just doing paper and pencil long division. So you ask yourself, does 34 go into 23? No, but how about, does 34 go into 230? Yes, it does. How many times? You might have to take a stab at it. I'm going to try 6, so I put a 6 up here. And then once I write the 6 up there, what is 6 times 34? That is 204, so we write it below, and we subtract. Remember this algorithm? This gives you 26. And then what's the next step? It's to bring down the next number. So now we have 266. So does 34 go into 266? Well, sure it does, but how many times? I'm going to guess 7, so I'm going to put a 7 up here, and then I need to multiply 7 and 34, and that gives me 238, so I write it below and I subtract. So what do we get when we subtract 238 from 266? We get 28. Now what do we do from here? Well, you may have done long division problems in which you just stopped at this point and you said that this was your remainder, so you might have written 67 remainder 28, or perhaps you wrote it as 67 with a remainder of 28 34ths, which of course could be reduced, but that's not the point right now. That's just another way to write the remainder. Or possibly you put a decimal point and a 0, or as many zeros as you wanted to keep going as far as needed, or as far as requested. So for what we're about to do today, we're going to focus on this method of writing the answer, putting the remainder over the divisor. Okay, so that relates to polynomial long division. Here's an example. We're going to take this polynomial and divide it by x plus 4. So here's how we do it. What we're dividing by, I believe that part is called the dividend, goes in the little box thing. Now I'm going to put a placeholder in there for my x term, so 0x. And then what we're dividing by, the divisor, goes on the outside. And what you do is you kind of ignore the plus 4 for the time being, and you ask yourself, x times what is 2x cubed? Or how many times does x go into 2x cubed? So x times what is 2x cubed? That would be 2x squared, and you write it up here. Remember from the previous one, once you write something up there, then you multiply it by the divisor. So 2x squared times x is 2x cubed, and you also multiply it by the 4. 2x squared times 4 is 8x squared, so you write that down and subtract. And I'm going to put parentheses around that to remind myself to subtract both of them and distribute that negative sign. Okay, so we subtract the x cubed terms and we get 0, and we subtract the x squared terms and we get -5x squared. What's next? Bring down the next one, and then go through the process again. So x times what would give me negative 5x squared. That would be x times negative 5x gives me negative 5x squared. And once we write the negative 5x up there, we multiply it by x plus 4. And that gives us negative 5x squared minus 20x. And then we subtract that. And that gives us 20x. What do we do now? We bring down the next one, and we go through it all again. So x times what gives us 20x? Well, it would be x times 20, so we put plus 20, and then we multiply the 20 by x plus 4, and that gives us 20x plus 80. And then we subtract. So now we have negative 86. So that's the remainder because there's nothing else to bring down. So what I can do is just write minus 86 over x plus 4. So that's what polynomial long division looks like. Now imagine if the remainder was actually 0. What would that mean for you? If the remainder is 0, that means something went in evenly, and that means you have a factor. So that's going to be a really important part of today's lesson. Okay, so let's try this one. We have a different polynomial expression, and we're going to divide it by x plus 2. So here's the x plus 2 on the outside, and then x cubed plus x squared minus 16x minus 1. Doesn't look like we need any placeholders. So x times what is x cubed? That would be x squared. And then multiply x squared by the divisor. We have x cubed plus 2x squared, and subtract. And that gives us negative 1x squared, and we bring down the next one. And then x times what is negative x squared, and that would be negative x, so we write it up there. Multiply it by the divisor, and subtract. And we get negative 14x, and we bring down the next term, go through it again. X times what is negative 14x, and that would be negative 14. Multiply that by the divisor, negative 14x minus 28, subtract, and we get 27. And there's nothing more to bring down, so the remainder is 27. So we can say plus 27 over x plus 2. Now, as you've probably noticed, long division is long in space and long in time. So can we make it shorter? Yes, we can. We have a shortcut for long division. Here's what we do. Use synthetic substitution to find f of negative 2 for this polynomial function. Notice that this polynomial expression on the right side of the function is the same as this polynomial expression in number 1. And notice that we're finding f of negative 2, and we had divided by x plus 2, which is x minus negative 2. Keep that in mind. So we put negative 2 in the box for synthetic substitution. Then we have 1, 1, negative 16, and negative 1. Bring down the first number, multiply it by the number in the box, write it down, and add. Multiply that by the number in the box, write it down, and add. Multiply that by the number in the box, write it down, and add. Notice these numbers we get: 1, negative 1, negative 14, and 27. So this is not a magic trick. If you think about long division, you had this repetitive process of multiply, subtract, multiply, subtract, multiply, subtract. And if you think about synthetic substitution, you have this repetitive process of multiply, add, multiply, add, multiply, add. But what we're adding here, negative 2, is the opposite of that positive 2. So it's like multiply, add the opposite, multiply, add the opposite, multiply, add the opposite, which is the same thing as multiply, subtract, multiply, subtract, multiply, subtract. So these processes give you the same results. It's just that synthetic substitution gives it to you in less time and less space. Now, if you are asked to do division, what you can do is called synthetic division. So synthetic division is only for dividing by linear terms. So only for dividing by things like x plus 1, x minus 3, x plus 7, x minus 2. Okay, you have a 1x, and it's not x squared, it's not x cubed. You could use long division for x squared, x cubed, other kinds of terms, but for synthetic division, it's only terms like this. If you're dividing by x minus k, you put k in the box. If you're dividing by x minus 2, you put 2 in the box. If you're dividing by x minus 3, you put 3 in the box. If you're dividing by x plus 3, you put negative 3 in the box. Then you do the same thing you do for synthetic substitution, as you saw me do. Don't forget, if you need the 0 placeholders, you insert them before you start. So let's try this. So we have a division problem, but instead of using long division, I'm going to use synthetic division. So if I'm dividing by x plus 1, I put negative 1 in the box. And the coefficients of my dividend go in a row. So 3, negative 2, 4, negative 3. Doesn't look like we need any placeholders this time. Bring down the 3, multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. Multiply by the number in the box, write it down and add. Now, in this context, we weren't asked for a function value, we were asked for the quotient that we get when we divide. So what we need to know is that this number is the remainder, this number is the coefficient, or excuse me, is the constant, this number is the coefficient on the x term, and this number is the coefficient on the x squared term. So that means we have 3x squared minus 5x plus 9 minus 12 over x plus 1. That would be our answer if it was simply a division problem. Let's do this problem. This one is not a division problem. This is find a function value. Okay, so remember synthetic substitution. If you're finding f of negative 1, you put negative 1 in the box, and then the coefficients of the polynomial go in a row. Notice I'm using the same polynomial that I used on number 3, so obviously we're going to get the same thing. But this time your answer is f of negative 1 equals negative 12. You just concentrate on that last number. Notice that the remainder, negative 12, is the function value, negative 12. If your remainder was 0, that means you found a factor, and the function value would be 0, and that means your point would lie on the x-axis. So your point would be an x-intercept, or a root. So here's the remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is f of k. In other words, the remainder that you get from division is equal to the function value, or the y value of the point. And then a corollary of the remainder theorem is the factor theorem. If you get a function value of 0, that means you got a remainder of 0. That means you found a factor. You found something that went in evenly. So a polynomial f of x has a factor, x minus k, if and only if you got a function value of 0, so you got a remainder of 0. If and only if can also be shown with a double-headed arrow. It's called a biconditional. Goes both ways. Okay, so let's use synthetic division to determine whether each linear term is a factor of f of x. So does it go in evenly is the question. So what we're going to do for number 5, if we're dividing by x minus 3, we put 3 in the box. The coefficients of f of x go in a row, 1x cubed, 0x squared, negative 4x, and 6. Bring down the first number, multiply by the number in the box, write it down and add. Multiply, we get 9, write it down, add. Multiply, we get 15, write it down, add, 21. So, did we find a factor? Is x minus 3 a factor? Well, is the remainder equal to 0? Nope, it's not 0, so nope, it's not a factor. Okay, try number 6 and 7, maybe pause and try them, and then resume. For number 6, we're putting -5 in the box. We have 1, 4, 0 for the x squared term, 16, -35. Bring down the 1, multiply by -5, write it down and add. 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 I got a 10. Hopefully I didn't do that too fast and make a mistake. That's not a 0. So again, we have no, it's not a factor. And number 7, we would put 5 in the box if we're dividing by x minus 5. We have 3, -2, -61, -20. Bring down the 3, multiply by 5, write it down, add, we get 13. Multiply that by 5, write it down, add, we get 4. Multiply that by 5, write it down, add, we get 0. Okay, the remainder is 0, so that means we do have a factor. So x minus 5 is a factor. And here's the bonus information. Remember how these numbers at the bottom represent your remainder, your constant, your x term coefficient, and your x squared term coefficient? Well, if x minus 5 is a factor, then you have another factor here. You have 3x squared plus 13x plus 4 is also a factor of the original f of x. Now once you get it to this point, if you wanted to keep factoring it, you could just try using normal factoring on the quadratic. Okay, we're wrapping up this lesson, but I just want to give you a preview of what's coming as we build to something bigger. So for graphing, it's important to have roots. Real roots are x-intercepts. When we graphed parabolas in our last chapter, we looked for the x-intercepts. X-intercepts and y-intercepts are important. In order to find roots, we're going to need to find factors. Factors are what end up with a remainder of 0. We're going to use synthetic division to help us find factors because it's difficult to find factors any other way when these problems get really, really complicated. So, the process of finding the factors for complicated polynomials, I'm going to call the root chase. Let's say we had a cubic polynomial expression like this and we wanted to factor it. What might you try? Do you think you would try something like x minus 3 or x plus 3 or x minus 4, x plus 4, something else? Why do you think I suggested those? Would it have anything to do with this number here? What other ones would be logical to try? So at this point, we haven't narrowed it down with any other skills besides guess and check. Let's take a factor, divide it in, see if we get a remainder of 0. So this is the same one, I just wrote it as f of x. Let's check to see if x minus 1 is a factor. So I'm going to put 1 in the box for synthetic division. The coefficients of the polynomial go in a row. Do synthetic division. Oh boy, found one right away. Look, the remainder is 0. So x minus 1 is a factor. Now, I don't want to mislead you into thinking that it's always going to be that fast and you're going to find one right away. It just so happened that this particular polynomial had an easy one. You might have to try quite a few before you find something that works. What if I had tried x minus 2 first? Then I would put 2 in the box. Wouldn't that be funny if this one also works? Do your synthetic division. Looks like it's not happening here. Whatever that is, it's not 0. So x minus 2 is not a factor. What I'll do now, though, since I know this video is getting long, is I'll finish the problem. So remember that what we have left here represents x squared plus 7x plus 12. So f of x has now been factored into x minus 1 times x squared plus 7x plus 12. And it just so happens that we can easily factor the quadratic part into x plus 3 times x plus 4. And if we want to find the roots, we're going to set each of these equal to 0, because roots are zeros and they are numbers that make the y-coordinate 0. We get x equals 1, we get x equals -3, and we get x equals -4. Does it surprise you that a cubic polynomial function would have 3 roots? And do you think that maybe a quartic polynomial function has 4 roots? And perhaps could it be true that a quintic has 5 roots, and so on and so forth? That's something to think about. Okay, here's your assignment from section 5.5. Thanks, everybody.